Welcome to Q&A Wire.
Okay, so in the first part of this problem, it gives us the reaction. So our reaction for this is going to be, let me find my pointer, Zn solid plus nickel 2 plus, that's aqueous, goes to Zn 2 plus, aqueous, plus nickel solid. And in part A, they want us to find the EMF under standard conditions. So we're finding E naught, or E cell naught. So what we need to figure out is what's being oxidized and what's being reduced, because remember, E cell naught is going to be the standard potential of the reduction reaction minus the standard potential of the oxidation reaction. So zinc here is going from Zn of the oxidation number of 0 to 2 plus. It's losing electrons, therefore it is being oxidized. Nickel is going from positive 2 to 0. It's gaining electrons. It is being reduced. So the standard E naught, the standard E cell for this reaction is going to be the reduction potential for my reduction reaction, which is nickel, which is negative 0.28 volts, minus that of the oxidation reaction, the zinc, which is negative 0.76 volts, to give me an EMF of 0.48 volts. So that's part A. That's the cell potential under standard conditions. In part B, we want to know the EMF in the cell when the nickel concentration, nickel Ni2 plus concentration is equal to 3 molar and the Zn2 plus concentration is equal to 2.1 molar. So in order to find the EMF under these non-standard conditions, we're going to use the Nernst equation. So I'm just going to write that over here. As a reminder, the Nernst equation is so the EMF is equal to the standard EMF minus, and I'm still under standard temperature, so I'm not going to worry about the equation that has the temperature in it, 0.0592. This is kind of the equation that's already partially solved. That's volts divided by N log Q. If you had to change temperature, you would need to go back to the equation that involves temperature. All right, so in this case, my E cell, my EMF is going to be the standard potential, which I calculated to be 0.48 volts, minus the 0.0592 volts divided by N, which is the number of moles of electrons, and zinc is losing 2 electrons, nickel is gaining 2 electrons, so this is a 2 moles of electrons in this case, times the log of Q. So Q, I'm going to come over here and write out Q. Q, remember, is products, not the solid ones, but aqueous or gases, so that's zinc 2 plus raised to the power of its coefficient, which is 1, over the concentration of the reactants. Again, solids don't count, so just the nickel 2 plus raised to the power of its coefficient, which is also 1. So this is going to be the log of the concentration of Zn2 plus, which they gave me is 0.100 molar, over the concentration of nickel, which they gave me as 3 molar. And you plug all of that into your calculator, and you should get and you have an EMF of 0.52 volts, which should make sense. Okay, why does it make sense? My EMF is greater than the standard, and it should be because I've added extra reactant. So extra reactant is going to push my reaction to having a larger EMF, as opposed to adding extra product, which should give it a smaller EMF because you're shifting the reaction left in that case. All right, in part C, I'm again finding the EMF under non-standard conditions, non-standard concentrations, where my nickel 2 plus in this case, I don't know why I keep trying to write E. Sorry, my nickel 2 plus concentration in this case is going to be equal to 0.2 molar. And my Zn 2 plus concentration is going to be equal to 0.9 molar. So in this case, they're actually both lower than standard conditions, which is 1 molar. All right, so again, I have E equals, and it's the same standard EMF, so 0.48 volts minus the 0.0592 volts, and it's still 2 moles of electrons, times the log. In this case, it's going to be my let's see, my 0.9 molar divided by my 0.2 molar. And for this one, again, you plug in all the equation or all the numbers into your calculator, and let me double check my number. Yep, and you should get that E is equal to 0.46 volts, so just a little bit less than my standard conditions.